Good morning, everyone. Please find your way to your seats. It's my pleasure to introduce Alexander Altland, who will be telling us this morning about late-time quantum chaos in low-dimensional gravity.
Okay. Can you hear me? Yeah. Okay. Yeah. First, thanks for the opportunity to be here at this wonderful workshop. Before I get started, I made a deal with the organizers. I get 10 minutes extra, but you're supposed to ask questions during the talk, not after. I mean, you can ask questions after, but please, if I try to be as clear as I can, but if I'm not, I mean, please interrupt me anytime. Yeah. So yesterday we had talks touching upon holography, quite a few of them, and I would like to seamlessly continue with that. Only that while yesterday the emphasis was on what one would call early time quantum chaos, I mean, scrambling and O-talks and so on, I will focus on the complementary regime of late times. Now, what does that mean? You all know, I mean, there is this arc problem in quantum gravity explaining the, if you want, the deep quantization of bulk microstates, quantum states in bulk gravitational systems, all the way from principles of semi-classical gravity. Now, as you push up there, I mean, you really want to probe fine structures of spectra. It means that you need to have control over very long time. That's what I mean by long time limits, yeah, in this business. Now, this is, of course, a super tough program, and it's unsolved in generality. But recently, there has been quite substantial progress in the toy context of low-dimensional gravitational systems. I mean, two-dimensional, a little bit of three-dimensional systems. And we owe this progress to the confluence of two principles. And the first is the holographic principle, and the second one is quantum chaos. Now, before saying anything more on that, there is one important additional remark I would like to make. The holographic principle in its orthodox form posits the correspondence between gravitational systems in d dimensions and some quantum shadows in one dimension lower. Yeah? And the emphasis here is actually on a singular correspondence between a quantum theory and a gravitational theory. The low-dimensional holographic principle is different in that the correspondence unfolds as one between a gravitational bulk and an ensemble of boundary systems. Yeah? And the nature of this ensemble, I mean, has been the subject of quite some debate and ongoing debate, and also some confusion. And this is center stage in this business. Now, that said, what can you expect from this talk here? I want to review these developments, assuming no previous knowledge. I'm a bit in a tight spot here because there are some, I mean, quite a few experts actually in this room, but I don't want to assume previous knowledge. So there's a bit of a compromise here. So I want to review this development, focusing on the nature of this gravitational ensemble, the way I understand it. There will be quite a bit of random matrix theory involved, and unusually for us, I mean, I'm a condensed matter physicist by training, random matrix theory from a topological. And on this basis, we would then like to discuss a microstate spectrum of 2D gravity. So there are checkboxes here. Take a pen and some ticks. If there is none, I mean, you have my full sympathy. The workshop is on quantum info and thermalization. There is none of that. Just a sprinkle of quantum info, maybe. So you didn't sign up for that. I mean, you feel free to do something useful. Yeah. For those who will continue to listen, yeah, here goes. I will start from a review with a review of the ergodic phase of quantum chaos. That's something many of you know very well. Sounds boring, but I will tell this story in a manner that is geared towards our later discussion of gravity. Then we will discuss semi-classical gravity. I mean, that's the physics of the ramp, if you want. For those who know the German. Finally, I want to turn to plateau physics, the deep quantum level. Yeah? This is more or less the outline. And let me now start with a quick review of, I forget gravity now, it's just about the ergodic phase of quantum chaos. A phase that is realized in all kinds of systems. You know that I personally think of it as the most universal phase we have in nature, actually. I mean, in classical physics, the most universal one is arguably the microcanonical ensemble. you quantize it, you generalize, you are at the ergodic phase of quantum chaos, and its universality reflects in that this phase is distinguished or characterized by just two pieces of phenomenological data. The first is that in this phase, quantum states are maximally random. There's a maximum entropy principle. They are Gaussian distributed over Hilbert space. Second, the spectrum shows a very high degree of order. The spectrum of chaotic ergodic quantum systems shows almost crystalline order. This is level repulsions. Levels are asocial, they repel, and therefore form, this kind of pattern, which we like to characterize in terms of statistical correlation functions. The most prominent of which is the two-point correlation function, simply measuring or probing correlations between density of states at a given energy and the density of states slightly, somewhere apart. And if you measure this distance here, this difference in terms of the single unit we have in this business, the average level spacing, which defines a dimension parameter of S, then these correlations are described in terms of correlation functions depending on the R of S. And they show an extremely high level of universality, reflecting the nature of this phase. There is actually 10 of them. We have to distinguish between 10 different antilinear symmetric classes of Hamiltonians, and each one of them has one universal of those correlation functions describing the ergodic phase. The fine print depends a little bit on the symmetry class, but they all have universal structures in common. First, correlations decay for large energy separation naturally, and they do that in terms of some power law. So there's an asymptotic series in this S parameter which describes correlations in a semi-classical regime, energies larger than the level spaces. In the deep quantum, we enter a regime that's non-analytic in F, the non-perturbative regime. And the distinguishing feature here are these oscillations. They tell about this crystalline order. Yeah? So this is this oscillatory structure. So that's the raw structure of all these. Yeah. Mm-hmm.
You have a very precise statement in mind.
That one here? Yeah. Well, all I'm saying that is if you are in this ergodic phase, means almost by definition states have, there's no structure left in Hilbert space, so they are uniformly distributed. Or maybe I'm misunderstanding the question. Yeah, but then you are not ergodic. Yeah. But if you, I think it's almost by definition, if you are ergodic, then it doesn't matter which spaces you have unitary invariance. It's a totally boring, super boring limit where everything is washed out. Oh. Good. You could click on a little. Yeah. Good. One remark. In many communities these days, it's more popular to discuss the Fourier transform of the core. And you all know this is the famous form factor where semi-classical physics short time large energies translates to a ramp. Then you have the plateau. And depending on the symmetry class, there can be a bit of drama here around this corner, but roughly this is the structure of this Fourier transform. So the deep non-perturbative limit is down here. Good. Now, we have these type of correlations are empirically, we know they are realized for all kinds of systems, and one can ask, how can this extreme level of universality conceptualize? How can we understand it? And there are two different approaches for answering this question. The first is, it's a stupid term, but I can call it the constructive approach, which is tightly related to the so-called Bohigaf-Giannoni-Schmidt conjecture, and it argues as follows. You argue here. Everything okay? Yeah? Good. So you argue as follows: if you have tons of systems which show this level of universality, they all have this in common. Then there must be a reference system, something like a harmonic oscillator of chaos, which already shows this as a proxy. Yeah. So it's a bit like saying in magnetic systems, if you have lots of systems that show ferromagnetic order or ferromagnetic phase transition, then there must be a simplest system, this would be the Ising model, which shows this behavior. This proxy is a random matrix Hamiltonian. Yeah? It's the maximum entropy, the most disordered Hamiltonian you can come up with, and it already shows up on ensemble averaging this universality in these correlation functions. And I want to, this is, by the way, in condensed matter and in many fields, this is the by far most prevalent way of describing universality. You say systems are chaotic if they behave like a random matrix. It's a bit tautological. It's a bit like when in gravity you say a vector is a vector if it's transformed like a vector. This is similar logic. Yeah? And I want to contrast this with a second approach where you argue as follows. If you have lots of systems showing the same behavior in the deep infrared, then they must reduce to a mean field theory or something. I mean, there must be a common mean field theory buried deep in them. I mean, it's like in this magnetic analogy, if you say the universal Ginzburg-Landau theory of magnetic systems is a phi to the 4 theory. Yeah, that's a somewhat different way of presenting this. And this mean field theory of quantum chaos exists. And it assumes the form of a matrix integral, a low-dimensional matrix integral. These Q's here are matrices of dimension 2 to 8, depending on the class. And the statement is integrating over these very low-dimensional matrices gives you these correlations. And these theories here are realized in all chaotic systems that are ergodic, and I don't know a single exception to that. This is the mean field theory of quantum chaos. Maybe, since there are many experts here in quantum chaos, who knows this theory? Hands up. A qualified minority, right? So this is not, I mean, at least in condensed matter physics, this is actually is a supersymmetric. This is a graded matrix here. For technical reasons, there are Grassmann variables involved. For condensed matter physics, this is often too technical. I realize that in the particle physics community has no.
Hi, I think there's no audio on Zoom. It just suddenly disappeared a minute ago. Sorry for the interruption.
Can you hear me on this?
Oh yeah, I can hear you.
Good, thank you. It's okay, no? Okay.
Yes, I can hear you. Thank you.
So we have these two resolvents, density of states, and remember the energies are slightly shifted. And let's now try to compute them. And the first that comes to mind is brute force perturbation theory. You expand an H and average over a Gaussian ensemble, say. And this then quickly leads, I mean, it's best organized in some diagrammatic codes, and the communities have invented diagrammatic syntax for that, which is slightly different. In particle physics, there is a preferred double line notation due to Post, I think. In condensed matter physics, we prefer this dashed line notation. This is old Russian 1950s textbook. I use that one here. It saves a little bit of paint, yeah, but this is just syntactical. There's no, but regardless of what we do, we encounter these diagrammatic structures. Now let's first look at the situation through the topology lens. Yeah? There you would do the following: you take your two green functions and you start expanding and averaging and get these kind of structures. And what you can do now is you can ask yourself the following, and that's classifying by topology: what is the genus of the minimal surface I need to draw such a diagram without any intersection of any kind? So this here, would, for example, would be a planar diagram. You don't see any intersecting lines. You just need a sheet of paper and you draw your diagram. Yeah? If you push on, you will encounter structures where you have crossings. And to accommodate these crossings, to avoid them, to draw this thing, I show you an example later on, you need, in this case, G equals 1, the torus, to avoid them. And so each of these diagrams in this series of ascending complexity gets a little tag. The G equals something which classifies as topological genus. So far, this is a totally useless observation, but it becomes very interesting when you observe, and that's now heavy stuff, that there is something like called topological recursion. You can classify these diagrams of ascending complexity and quantify them, their total contribution to a correlation function, hierarchically in terms of diagrams of lower topological complexity. This is a high-powered machinery known as topological recursion. It's early 2000s. And in this way, you can write down formal sum representations for your correlation functions. I don't think, please correct me if I'm wrongly expert, that these are particularly useful when you really want to get answers. Yeah? The correlation function has this and that power law behavior, but at least, conceptually, there is this kind of dimensional topological hierarchy here involved. And have it in mind, it will be extremely important later on when it comes to gravity. So this would be the topological view of the situation. Now I'm switching gears to condensed matter view. Here you are solidly interested in powers of this guy. Yeah, there's slightly different energies. You want to know what is the scaling of. How do I extract these relevant singular scalings of diagrams? And in condensed matter logics, you need to sum perturbation contributions to perturbation series of very high regularity, with ladder structures, to get something which has a chance to be singular. So the leading order term in this series, always S inverse squared, S was the energy difference, remember? And that's the ramp actually here. Comes from these very highly regular ladder structures. Physically, these are processes where retarded amplitude and in advance propagate along the same sequence of scattering events in the Hilbert space. So they give you this ramp behavior. And now you can push on and write down more complicated diagrams. So this would be a ladder diagram giving you S inverse third, and you go on this way. Yeah? And you try to, and this has been an industry in condensed matter physics, in quantum chaos. Now we have two views. This one here, this perturbative diagrammatic extracting correlations into topological, and they are or must be related. The simple observation is that each of these diagrams is a diagram and therefore carries a topological genus. Yeah, we learned that before. So this is obviously here genus 0. It's a planar diagram. This one here is a genus 1 diagram. You need a torus to draw it. So you have this correspondence. You have, on the one hand, you have the singularity degree and you have the topological degree. And interesting, this is a very strong statement, very useful. The genus degree actually matches the singularity degree. So if you have a diagram of S inverse 7, you know that it's a G equals 7 diagram. So there's a very strong, I don't actually know, maybe some mathematics involved, but this is an observation, and it's extremely useful. So you can think of it as follows. You have these baskets of diagrams of increasing genus. They're getting more and more complex, and embedded in them are subsets. These are these highly regular diagrams, which are not only topological of a given degree, but also singular in S. The majority of diagrams has no S singularity, but some of them have, and they are embedded in here. Or conversely, each diagram contributing to the expansion of the ramp has a certain topological degree. That clear? Halfway? Yeah? Good. So that will be important. Final remark. if you look at these diagrams, they resemble like diagrams of the expansion of some kind of quantum field theory. Like look like effective quasi-particle propagators. This quantum field theory, giving this diagrammatic expansion, what features should it have? First of all, it must be zero-dimensional. There is no space here involved, no spatial structure. We are ergodic. And second, it must be massively nonlinear, because you have all these interaction vertices around. Yeah? And this is precisely this effective theory of quantum chaos, what it does. So if you integrate here over these matrices, which are nonlinearly realized typically, and do perturbation theory, expand them, and for large S, you generate a diagrammatic expansion, and this is precisely these are these diagrams. So this is a very efficient way, maximally efficient way of getting this series, but also doing non-perturbative stuff, because this integral can be done for arbitrarily small s, and if you do it, you get the non-perturbative contents of the correlation functions as well. Yeah? So this is the end of this. Last remark. I mentioned that there is a sprinkle of information here, yeah, just a little bit, and that goes by the name symbolic dynamics. What you can do is, and this goes back 100 years, I mean, it's a very old idea. You can simply write down a list. You label the scattering events in the Hilbert space, and you write down their chronological order. So here you scatter A, B, C, and so on. And you always have two trajectories involved. So you have two codes which you can compare. And what the symbolic dynamics can be set up for all diagrams. So you can, in principle, at least in principle, you can encode their contents in writing down such a list. So in a way, this diagram is just another way of doing the bookkeeping of the order of scattering events in your Hilbert space if you want to get something that's phase coherent. Yeah? And that's that. So on that basis, we now turn finally to this gravitational part of the story. This is, just the motivation again. So there was a traditional holographic paradigm. And then at some point, what came into the foreground is that black holes are actually chaotic system, and that arguably motivated Kitaev as of 2015 to ask the question, is there a maximally simple implementation of this holographic idea in the lowest possible dimension, namely two-dimensional bulk, one-dimensional boundary? And I'm fast now here because I guess you've heard that before, for example, yesterday. So the candidate boundary model was proposed was a Majorana SYK in this case. It ticks in lots of boxes. It's one-dimensional. It's quantum mechanics. It shows hard quantum chaos at all time scales. It's maximally chaotic. And it has it's almost realized conformal invariance built, so it's a bit like ADS-CFT-ish conceptually. And here's, plots. The correlation functions and all that are properly random matrix-like. And in particular, we've shown that this effective field theory, which I mentioned, is in the SYK on the near field level. So at low energies, you can reduce the SYK Hamiltonian, the G sigma partition sum or something like that. You can reduce it to this field theory. How should we think about this holographic correspondence if you haven't seen it before? Here goes. So you look at an SYK partition sum, and you can think of it in two different ways. One is you consider this as the imaginary time Fourier transform, so it's a time Fourier transform of a propagator, resolvent as we had before, only that this is now the SYK Hamiltonian. Alternatively, you say this is imaginary time, it's a circle. Yeah? And if you want to think holographically, you then want to interpret this circle quantum theory as a boundary of some gravitational theory in some two-dimensional bulk. So far, so obvious, but now it's getting more interesting. In quantum chaos, a single green function is almost always trivial. It's everything is in correlations. We discussed it before. So if you consider now two of these theories, you can run this paradigm for each of them, and naively you would think that you end up with this situation, but now you immediately run into a problem, because if you average over this order, everything is in correlations between these two. The entire physics sits here in correlations, while if you have two disconnected surfaces, they don't talk to each other. Yeah? That's at least the way I think about it. So there's a problem with this view. But what holography instructs us to do is to consider all surfaces having a given boundary, in this case, 2 boundaries as a limit. And that leads one to consider these guys. So these annular, and they are known in the parlance of the field as Euclidean wormholes. And we should do 2 things. First, we should decide what theory to put on them. And second, we have to consider all geometries that have these guys as boundaries. Yeah? So this is a general setup. The next question to ask then was which theory to place there, which actually has, at least in an approximate sense, is SYK correlations as boundary data. And the answer was, you've seen it, I was also mentioned yesterday, the answer was Yakif Teitelbaum gravity, which is 2-dimensional gravitational functional, described by a 2-dimensional gravity functional coupled to a scalar field, the electron field. So that one does the job. And the question is why? We know the answer because there are 2 bridges actually exist between this SYK boundary theory and the JT. The first is operational at low time scales. This was mentioned repeatedly yesterday. This is time scales of polynomial in the number of particles of the SYK. That's the Schwarzian action. And so the Schwarzian is a common low energy action in this time domain for both the SYK and JT. But there exists another one, and that's the one which was not mentioned so far, which we actually owe to mostly people here in this room. And that's one operating at much higher, larger time scales. Not quite, but getting close to the Levit spacing time scale here. And this is now based on an implementation of the S-inverse expansion I mentioned previously for the random matrix Hamiltonian for these 2 in this setting. So let me quickly comment on how this works. For that, we need to take, now we're in gravity land, yeah? We want to see how can we get something akin to a 1/S expansion from a gravitational theory. So it all starts with an integral over, or the functional integral representing this gravitational theory on. And what you need to do to set it up is first, remember, we have to integrate over all surfaces. We're now talking about an integral over geometries. So first you classify according to topology. You just label them topologically. And for given topological data, you then have to integrate over the fine print of your geometry. But thanks to the nature of this gravitational system, this is relatively simple. You have constant curvature on average, so that simplifies this program. And what you get is an integral, is a sum over these topologies and then integrals over these residual data. So that's the raw structure of your gravitational theory. And now we have a super important concept. There is again a topological recursion at work. Namely, you can, that's at least my limited understanding goes as follows. You can classify contributions to this very complicated sum hierarchically, in that you describe higher order contribution of higher topology hierarchically in terms of lower dimensional ones. And that we owe to Mirzakhani. So that is a topological recursion in gravity. And this was then made subsequently quantitative in that this gravitational topological recursion was compared to the matrix topological recursion I mentioned earlier for a matrix model with a certain, with the density of states fine-tuned to that of the SYK. We take a matrix model, cook it up such a way that its density of states close to the boundary, this is all infrared physics, close to the low energy limit, matches that of SYK, formulate topological recursion for that, now in matrix land, and you obtain a perfect match. Do I have it right? I mean, this is more or less the story. Okay. So this was the content of a super influential paper by these 2 gentlemen over there at the start. And that's an extremely important result, I think. It shows that this quantum chaos, asymptotic expansion we have before, it's actually realized in the gravitational context, and it applies to all diagrams, and therefore in particular to the singular ones. So this gravity theory is we know now it's at least semi-classically, perturbatively, it's chaotic. and it gives us this ramp contribution to correlations. So far, so good? Okay. Now, in a way, this correspondence beautifully works. It doesn't work on the level of final result. It works diagram sharp. So each chaos diagram has precisely one gravitational match. So we have, I like to think about it as a kind of a Rosetta Stone. Yeah, I mean, really matching these two. And for a quantum chaos person, this is important. We have several of these library entries where, for example, between Floquet Hamiltonians and periodic orbits. I mean, for each of them, you have such a diagrammatic code. And we have a dictionary, and now we have one more entry. So this is very nice from this perspective. I would like to give you some intuition on how, I mean, at least how I think about it. How do you connect between diagrams and surfaces? And I can do it as follows. Remember, before we had this topological classification. Here I'm drawing two diagrams. One is genus 0, so really this is genus 1. And you can draw them now, simply redraw them in such a way that this genus nature becomes more explicit. So here you see this one drawn on a surface, it's planar. This one is this diagram here, which is an S inverse cube guy, I think, drawn in such a way that I've tried to draw it on the toe, so there's no intersection here. Yeah? And now you imagine these red and blue, you imagine them as boundaries, you pull them apart, you think of the structure made of rubber, and end up with this. So here you have your simple Euclidean wormhole, and here you have an inclusion. There is no intersection here of these lines. So these lines now, on the one hand, they encode, this was a symbolic dynamics view, they encode the information on the sequential order of scattering processes. And here the same information is encoded in the geometry of the surface. So it's like geometrizing information. Another way to think about it, and this is less silly than it may sound here, you can think of them as some kind of strings. Yeah? So these dashed lines have become strings, and that will become more serious in a minute. Good. So that is about as much, I think, as one can say about the perturbative expansion of this gravitational quantum chaos. We have this part under control now. But now you can ask, what about this one? The deep quantum. So it turns out that in certain and extreme limits, I mean, level spacing close to the edge of the spectrum, one can apply an ingenious resummation of the diagrams to get some information about this. But in general, one needs to do something more. I mean, to add something conceptually to the story to understand here this type of the correlation part. The second question you can ask, where is this gravitational ensemble? I mean, so far we have seen these surfaces, but we have not seen any, I mean, we have not really made clear where's the nature of the boundary ensemble, how does it reflect in the gravitational bulk, right? So these are two questions one can ask. Further to what I said so far, and I want to argue now that they both have a common answer. If we think about gravity as a semi-classical limit of a string theory. And now I'm out of my comfort zone, I'm condensed matter physics, but I want to make this here as concrete as I can. In the remaining, how many, 10 minutes, how about? 2 minutes? Yeah, fine, that's okay. So why should one maybe think about string theory in this concept? So remember, I mean, string theories, they tell us that gravitational theories are semi-classical limits of springs. The way I think about it conceptually here is as follows. This was the stuff we have been integrating over in our gravitational path integral. And think about it really as a path integral of some quantum theory. So what this quantum theory should describe, I mean, if you think about this here as really probabilities, it should know about scattering amplitudes where such closed strings here, if you want, scatter into multiple closed strings. So they're called mini universes in the parlance of the field. So we're thinking for a quantum theory which has these processes here as elementary scattering processes. And that's some kind of as I will comment, is a closed string theory sitting in the background. But then there is something else. In string theory, they have this very important concept of closed-open duality. So if you have a closed, if you want to think about it as a closed string here for a moment, propagating and tracing out a worldsheet, you can exchange coordinates, space and time, and alternatively think about it as an open string propagating in this direction. So this is the nature of this duality. And this sounds like a bit, I mean, metaphysical now, but I want to make it now concrete. And I want to draw your attention to the superficial resemblance of these guys to these impurity lines. So the thing is that this picture can be made very, very precise. And it goes like this. This is how all worked by, I think it's due to the Eric, right? It's Eric Berlinde, essentially Amsterdam group who did this first. I mean, I don't know, maybe it's older. But what you can do is you can understand this two-dimensional gravity with a dimensional reduction from a higher dimensional manifold. A Calabi-Yau manifold, a six-dimensional manifold. So there's a controlled dimensional reduction scheme going down from this geometry down to a two-dimensional theory, which is known as Kodera-Spencer field theory. That's technically a 2D conformal field theory. So this conformal field theory has a cubic nonlinearity built in, and it is such that if you evaluate it in perturbation theory, order by order, you get the JT partition sum results. Yeah? So this one, it's a string field theory technically, and its perturbative evaluation gives us the semi-classical gravity. Let me know. It gets important when you observe that there is, besides this one-dimensional, one root going down here, which emphasizes a closed string perspective in the language of string theory. Oh, shit. There is, sorry. There is a second way of descending, which emphasizes open strings. It's just another way of executing this program, and they are related by a closed open string duality. And what you encounter here is so-called large stacks of branes, compact branes. So never mind what they are in detail. But what's important, I mean, branes in string theory are connected by strings, right? And these open strings connecting these guys, we have to integrate over this entire package. Just think about it as hidden degrees of freedom you need to integrate out in order to go down. And they realize this ensemble. They are mathematically, really down to details, equivalent to a random matrix ensemble. So integration over these string degrees of freedom, open strings, implements an ensemble which then condenses to the theory after dimensional reduction, and that gives us JT. The final remark is that this Kodera-Spencer field theory can be analyzed on the mean field level, and it reduces exactly to the effective field theory of quantum chaos, which I mentioned before. Yeah. Yeah, sure. Yeah.
Where is the randomness coming from?
That's actually about, so you're an expert. First of all, you have lots of, just accept this, you have lots of degrees of freedom you have to integrate over in executing this program. So now, in our language, this would be a bit like an annealed average. Yeah, you integrate over dynamical degrees of freedom. But it's actually mathematically equivalent for reasons which I do not entirely physically understand to a quenched average. So this is your ensemble. And there is a bit of mystery involved. There is some supersymmetry here, so it simulates a quenched average, and I don't understand this very well intuitively. But by quantitatively, it really plays a role of a random matrix ensemble. And yeah, no, last remark is this 2D CFT on the mean field level, it reduces to the effective theory of quantum chaos. So just to flash this, I mean, this CFT, you can compute operator expectation values which give you these chaos correlation functions. So some CFT.
questions. So who would like to start?
Can I have a question? Sorry, I couldn't see the audience, so I don't know if I interrupted other people's question. Can you hear me?
Okay. Yeah. Yes. Please. Please ask your Zoom question.
First of all, the audio disappeared for half second, for like 10 seconds. So I hope this is a question time, right? Sorry, I'm not interrupting you in the middle of the talk.
Yes. No. This is a perfect time for questions.
So I didn't get why there is a genus expansion in these diagrams. So in the matrix models, we to get a genus expansion, we need like the lines and the loops, and these all scales in correct powers of the same large number. How is that achieved here in these diagrams?
I think the question was where does the genus expansion come from? Is that the question?
Yeah.
Yeah, like why these diagrams satisfy genus expansion? Can you hear me? Yeah. But I don't think I hear Alexander.
So you mean this story here that wait a second. Just a sec. You mean where these genera come from? I mean, why these singularities at the same time as an expansion in singularity and in topological genus? Yeah, is that the question?
Yes, yes.
Yeah, I don't understand it. I'm sure there is a mathematical principle behind it or reason, but I just don't know it. But what I know is how to actually identify the genus of these guys on the level of individual diagrams. And it's an empirical observation that the degree of singularity matches the genus. I don't know. I also asked a few other experts in this field, and nobody knew. I mean, maybe somebody here knows. For me, it's an empirical fact.
I see.
So why? I'm absolutely sure that there are people on the planet who understand why the perturbative expansion of a nonlinear sigma model in 0 dimensions is a topological expansion, but I don't know.
Okay, thanks.
Yeah, so there's this, you described the Hilbert space in this Kadara-Spencer, sorry, the ensemble in the Kadara-Spencer theory is coming from these open strings between branes. There's a there's a very gravitational geometric perspective where the ensemble corresponds to the Hilbert space of closed universes, and a wave function of closed universes corresponds to a probability distribution on the space of dual theories. Is there some sharp connection between those two pictures? That
I don't know. The thing I'm personally convinced of is that this integral over smooth surfaces is a result of an ensemble averaging. So this is an ensemble average theory. And the microdata, my personal view, I'm happy to stand corrected. The microdata you need is included in this reduction program in the integral over these stacks of degrees of freedom. You know, we have the calculation in front of our eyes. We see how it works, and you can really look at it line by line. It's ensemble average implemented, and it leads to the JT partition sum.
So, for example, in the Kadara-Spencer theory, can you do something, change the state of the theory, or so to deform the ensemble, or even to pick your wave function to be peaked on one member of the ensemble, pick out one specific Hamiltonian?
Yeah, very good. So in this Kadara-Spencer theory, there is some input you put in by hand if you want. This is the so-called spectral curve, the density of states of your theory. Once you have that, you have fixed everything, and you have no more rooms to maneuver left. And there's one more irritating thing. Which is, we know all to calculate in this theory only spectral determinants. So we can't do anything more intelligent, like for example, we would like to compute states or operator expected. We don't know how to do that. And I think nobody understands. Yeah.
Alex, is it your understanding that this Kodaira-Spencer theory is non-perturbatively well-defined? That is, it's some integral, path integral or something we could stick in a computer. I mean that there are no ambiguities. It's.
Oh, that you should ask Kumrum Waffer. But at least okay. I know two things as a fact. First, it has this perturbative expansion.
Yes.
This is not what you're getting.
Right. Yeah, that's right.
Perturbatively, it produces an asymptotic series. And second, I know that if you ask it these questions, these determinant correlators, and you compute them, you get without approximation nothing. You get this Efetov nonlinear Zika model, and that's totally controlled.
Yeah, I guess we know that the matrix integral, is in this double scale version is got some ambiguities in it.
Yes.
Like there's contour choices you have to make. And so it seems like that data has to be present in the complete Kodaira-Spencer theory.
Right. So what they did is, I mean, I tried to say it before, they stick in this spectral curve,
right,
which reduces to the sinh square root of epsilon. I think you're referring to at the boundary, but now I guess you're asking what does it do for larger energies, or
well, or maybe even in the forbidden region, like where these one eigenvalue instantons are.
I wouldn't. I mean, I don't want to say anything wrong, so I.
Okay. All right. Thanks.
Yes. So when you were drawing the diagrams on different Riemann surfaces, and then you pulled the red and the blue lines apart. So can you elaborate a little bit more on that? Should I think of these red and blue lines as really the asymptotic boundaries in the gravitational description? And what does it mean when you were drawing these things on, when they were closer together, or like do you have some geometric?
No, I actually Julian Sonner always told me that this meaningless exercise, but I sat down with my iPad and I wanted to draw these things. So the thing is, I understand the diagrams more or less topologically, and I simply wanted to relate how it connects to the surface, to the geometry of the surface, make it explicit in front of my eyes. And so it's no more and no less than that. I mean, you have zero intersections in these things, so they have this mesh of parallel lines, and it simply makes explicit the topological degree of the surfaces. And yes, I mean, the boundaries are the boundaries. At the boundaries, I think about it as a quantum theory undergoing a sequence of scattering events, and they are correlated.
Yeah, but in JT gravity, you actually have some hyperbolic metric on
no,
these.
This doesn't know about metric. This is just topology. It's only the topological content. To get the actual, to get this quantitative matching, you have to invoke more refined data, namely the actual density of states of the boundary theory and these moduli space geometries determined by the action, by the non-topological part of the action. That's the way I understand it.
You know, it's more precise in it. Like if you've got this very low temperature limit, it's whether the boundary is becoming very long in units of the ADS rate or in the curvature radius, and so all these surfaces degenerate into sort of thin ribbons that are connected that are very, very. And so there is some metric structure that's related to sort of how many rungs in these ladders there are and so forth.
About metric, I don't know, but I think what you're alluding to is that in this long time limit, this whole machinery of diagrams reduces to these ribbon diagrams, and then you can draw the similarly minded picture by perturbative expansion of the Kontsevich model, which in turn reduces to the nonlinear Zika model in the limits I'm considering here. So this all checks out. Yeah.
So for the GUE case, I guess these singularities cancel out, right? Is there a perspective from the perspective of these diagrams that makes that obvious?
Why they cancel out? No, we simply know. Yeah, I mean, okay, this nonlinear Sigma model, whose perturbative expansion produces these diagrams, right, is semi-classically exact. So there's a localization principle. We know it. It can be evaluated exactly in a stationary phase, which is just a simple stupid ribbon diagram. So all the other guys, we know about them, they do exist, but we know beforehand they must cancel out term by term. But this cancellation is quite non-trivial. I mean, you get all kinds of diagrams and they all sum to zero. In this case, as you know, I mean, you have not been there in other classes, it's different.
There's some twist about Heckman being in the signal.
Okay, physically in the GUE case or in all beta equals 2 ensembles, I think 4 of them, you have an exact ramp. So there is no perturbative correction. And in this language, the underlying reason is a localization principle of these corresponding nonlinear Sigma models. And yeah, I mean, that's what I try to. So you know beforehand that everything must cancel out, but cancellation itself is actually instructive.
In terms of these encounters, it's some sort of miracle. Do you have an understanding of the miracle?
It leads to the cancellation?
Yeah.
No. No, I think nobody has. I mean, these are the encounter diagrams, right? They are just the encounter diagrams for the random matrix.
Any other questions from the audience? All right, well, if not, then maybe we'll break for coffee and thank Alex again.